Okay, we're starting. Uh, Actually, we're going to be addressing Lagrange multipliers. We're going to start out with asking you to sketch the z equals 0, 1, 4, and 9 contours of the elliptic parabola z equals x squared plus 2y squared. Okay? So some of you are off on the wrong track. The very first thing you probably want to do with this is write the equations of these contours, which would be like x squared plus 2y squared equals 0, x squared plus 2y squared equals 1, x squared plus 2y squared equals 4, and x squared plus 2y squared equals 9. Now, maybe you don't write all those out. Maybe you know that those are going to be the equations, and you write them out one at a time and work them out, okay? But you probably want to start with the equations. It doesn't hurt to start by sketching a coordinate axis, but since you don't know what's going to go on the coordinate axis, I would just say that the approach here would be to first understand what the contours are, okay? And then write out the equations of the contours. So that should clarify that part. Each of these is an ellipse, right? Okay. So you can then work out the equation of the ellipse. Now, some of you are trying to do a straight line with a slope of 1/2. Okay. If it was x plus 2y equals 0, that'd be exactly right. So, you know, it's not a purely bad thought, but it's x squared plus 2y squared. And the only way x squared plus 2y squared could be 0 is if both x and y are 0. Because neither of these numbers can be negative. Okay. So there we have it. So you could start your contour sketch by saying, well, first contour is just this point. It's the origin, right? Now, what's the second contour? X squared plus 2y squared equals 1. That's an ellipse with semi-major axis of 1 on the x-axis, on the x, semi-minor axis of square root of 2 over 2 on the y. It's going to look something like this. Or if you wish, this is a line x equals 1. This is a line y equals the square root of 2. Well, we'll just say 1 over the square root of 2, which is approximately 0.7. And that rectangle should be a rectangle. It's not, it should be centered at the origin. So let's go ahead and cut it off here. X be -1 here, and so forth. And then your ellipse. I've drawn this, it's distorted. It wouldn't be a circle, it'd be a little flatter, be longer in this direction than it is in this direction. Okay. Now, what happens if you go up to 4? Well, you should review conic sections if it's not clear. A lot of you writing out the right stuff. You write out the equations and you put the conic sections into their standard form. Just taking the x squared plus 2y squared equals 4. You put it in standard form, which is x squared over something squared plus y squared over something squared equals 1. And then the somethings that are squared are your major and minor axes. So your next one would be, your next rectangle would be out here at x equals 2 and x equals -2 and y equals the square root of 2. And you're going to have a bigger ellipse. So you're going to have a series of ellipses. And since the numbers here are perfect squares, they're all going to be the size will always be multiples of the size of the first one. The second one will have twice the dimensions of the first. The third one will have 3 times the dimension. Actually, the first one's just a point. So it's 0 times the dimension of the second. Okay, well, let's just say these are contour lines. You plot the line now. Let me think a minute. Let's just plot the line y equals x minus 1. I'm going to go a little lower than that. Let's go y equals x minus 3. Where's that line going to go? First of all, this is a contour for z equals 1. This is a contour for z equals 2. This is a contour for z equals 3. Sorry, 1, 4, and 9. This line here would be for y equals 3. No, sorry. This line would be for x equals 3. And this isn't drawn very well to scale. Here would be x equals negative 3. And this line might be y equals about negative 2.1 here. Y is about 2.1 here. That's its information. Where is the line y equals x minus 3 going to go on this picture? You can graph this line easily using its x and y intercepts, right? X-intercept occurs when y equals 0, because that's what the x-axis is. It's a line y equals 0. The x-intercept is then, if y equals 0, you solve x minus 3 equals 0 and get x equals 3, right? Of course, you can just do that by inspection, but you're going to go through this point here. And the y-intercept occurs when x equals 0, and if x equals 0, you get y equals negative 3. Well, if y equals negative 2.1 here, it's negative 3 here, and now here's our line. Oh man, look at that. I didn't intend for that. It looks like that line is tangent to this second circle. I doubt that it really is, but it looks like it. Okay, does that make sense? Let's say these z values are temperatures. So right here, z equals 0. On this curve, z equals 1. On this curve, z equals 4. On this curve, z equals 9. let's say these are Celsius temperatures, so they're at least reasonable for this time of the year. Okay, so here's freezing, and here's a temperature near 50 Fahrenheit. Okay, be 48 and 4/9. Okay, so this could be a reasonable range of temperatures, but these are probably not temperatures throughout a day. Okay, the day's somewhat cooler today. Have some days like that next week. Days are pretty warm this week. Actually, it's almost 2 weeks. Well, a week out. Okay, about 9 or 10 days, I think, it's supposed to cool off. But just to relate to the temperatures, now let's say that these represent temperatures on a plate. Okay, let's say that the whole plate was originally at 12 degrees, and then we decided to freeze this one out. Okay, so the points further from here stay closer to 12 degrees. They didn't lose heat as much as the ones closer to the center. Okay, we just apply something really cold at this, do something to bring the center quickly down to 0 degrees. Okay, and then let the heat flow for the rest of it. Okay, so these could be temperatures getting warmer as you move out from the center. Now let's say that you're a cold-loving creature walking along this line. Where is it you're going to hit the minimum temperature? All of that. Okay, we're talking back and forth on this. People are slowly coming around to being oriented to this picture. Okay, these are temperatures. So I point here and ask, what's the temperature? You know, this might be where X is negative 1.5 and Y is 1.3. Okay, something like that. But what's the temperature here? It's 4 Celsius. If you think of this as Celsius temperature. Hopefully it's not absolute temperature because nothing's going to survive it down 4 degrees above absolute zero. No. Okay. Helium doesn't quite freeze there, but it's getting close. So Z equals 4 everywhere in this contour. What's Z here? Well, we eventually got an estimate of 9. It's between 4 and 9. An estimate of 7. It's between 4 and 9, and maybe closer to 9, maybe not. But we get the idea. It's getting warmer as we move out. And we have the temperature on each contour. Okay? Now, that all comes from the question, if you've got a cold-loving insect, I don't know if there are any, okay? Maybe something that lives deep in the ocean, where it's cold. But you've got a cold-loving insect that's traveling along this line, starting down here and moving up here. So what is it going to experience? Somebody said, well, temperature changes. Okay, yeah. That was good. Can you be a little more specific about how the temperature changes? Well, think in terms of the bug's happiness. Okay? As the bug starts moving along, is it getting happier or sadder? It's getting happier because the temperature is dropping. You're crossing one contour after another in the direction of lower temperature. The contours are for lower and lower and lower temperatures as you move along here. You cross the contour where the temperature is 9, and then you're moving toward the contour where the temperature is 4. Maybe you actually hit that. Maybe you actually cross that contour and get down to temperatures a little less than 4. This is an approximate sketch, and just coincidentally, totally coincidentally, this thing is tangent here. Okay. But I'm kind of happy about that. Okay. Wasn't intended to be that way. But there it is. Okay. Now, so far the bug's happiness has been increasing. What happens next? It gets less and less happy, but it's not smart enough to stop. Poor bug. Eventually, it'll catch on and maybe it'll start oscillating back and forth and come down to some point. And you can set up a differential equation, analyze the oscillation. Okay? Or isolate the oscillation. Oh, no, that's right. Okay. Make sense? So here is the optimal point. For our bug. Remember, the bug loves cold places. Okay? Now, the only reason our bug is going to travel along this line is if it's constrained to travel along the line. It's got no choice. This is the only path that it has. Maybe if it veers from this path, something's going to get it. Okay. If it wasn't constrained and it started here, it would probably curve in to this point or maybe spiral in, depending on how bright it is. Okay. And there's another interesting differential equation that you can solve and do kind of a direction field and all that stuff. Okay. But this isn't differential equation class. So this poor bug is constrained there. Okay, well, what we have then is that bug wants to optimize, which means it's going to minimize in this case. I'm going to use capital T, just remind us that it's temperature. Subject to the constraint y equals x minus 3. Okay. The optimal point will occur when the constraint path is tangent to one of the level curves. Okay. That's the key thing to understand about the geometry of this situation. So we're building up to Lagrange multipliers. And people find deep problems in Lagrange multipliers to be pretty easy. It's just a simple algorithm that you follow mindlessly and get the right answer without understanding anything about what you do. That's entirely possible. Okay? To the extent that you have time and other factors, you want to understand this in terms of the picture. You want to understand why it's so, which is what I'm talking about. The method itself is easy. I mean, the algebra might get tough, the derivatives might get hard, but the process is very simple. It's, well, when I say very simple, it's about a 5-step process. With practice, it becomes easy to do it whether you understand it or not. Okay? Well, now, this means you can look at it two ways. This direction has to be parallel to the tangent vector. Okay? The vector tangent to the level curve. Turns out to be easier in general if you say the direction perpendicular to this line is perpendicular to the level curve. Okay? A direction along, I just said direction perpendicular. I think maybe I could have written that down. The direction perpendicular to the constraint path is also perpendicular to the level curve. Now, why do I want to talk about perpendiculars to the level curve? Well, what's perpendicular to the level curve? The gradient. Okay? So, okay. Now, in this case, and I'll do this case before I do the general case. What's perpendicular to this straight line? What's the direction perpendicular to the straight line? Well, it's always the direction with negative reciprocal slope. Slope is -1 in this case, because the slope of this line is very simple, it's 1. So this slope is -1. So let's do that as a vector. It's I minus j. Make sense? Okay, well, what's the gradient of t? Can you calculate the gradient of temperature function here? X squared plus, it's 2y squared. What's the gradient of t? Write that out. Okay, forgot to turn on the camera, but let's see where we are. We've said that the optimal point is where the constraint path is tangent to the level curve, and that's true. Well, if the constraint path is tangent to the level curve, that means parallel to the constraint path means is the same as parallel to the level curve, which means perpendicular to the constraint graph is constraint path is perpendicular to the level curve. Where they're mutually perpendicular, well, that's going to occur. What's perpendicular to the level curve? Well, if our level curve is t, which is the x squared plus 2y squared function, then the gradient of t, incidentally, okay, that's a vector operator. The gradient of t is perpendicular to the level curve, obviously. Again, I think I was just saying that. Okay. The geometry is the constraint path should be tangent to the level curve. That's going to occur where perpendicular to the constraint path is perpendicular to the level. Perpendicular to the level curve is a gradient. I'm sorry, perpendicular, to the level curve is the gradient of the target function. Okay, the temperature function in this case. And perpendicular to the constraint path, we'll do that in a minute. The formal way you do this, if it's not a straight line, but in this case, the constraint path is a straight line with slope 1, perpendicular to that's a slope -1. Well, you translate that as a vector, I minus j. Okay? So I'm just going to say that perpendicular to the line y equals x minus 3 is the vector I minus j, or 4i minus 4j, or 78i minus 78j, pi a minus pi j, anything where the I and j components are equal and opposite. Any vector will do. The gradient of t is 2xi plus 4yj, which is very straightforward. I've done that down here because some people were having a little trouble remembering what a gradient was, okay? That won't be a problem when you've worked through all your assignments. It's very simple calculation. You do it a lot. When I say it's simple, it's not always simple to take the derivatives. Some of them are pretty hard. But for most of the problems, you're going to see the derivatives are pretty simple. Okay, so there's your gradient. So my question then is, where is this gradient parallel to this vector that's perpendicular to the level curve, to the constraint path? Okay. That's going to be the case if the vector, if the gradient vector, the temperature function, is constant multiple of the vector perpendicular to your constraint path. You can write that as the gradient equals lambda times the perpendicular to the constraint path. That means it's constant multiple. Lambda just happens to be a multiplier. It's an arbitrary symbol that everybody in the universe uses. Okay? I think they even use it in the Andromeda galaxy. Okay, there we have a simple equation that's very easy to solve now. You solve this for lambda. Well, actually, you can do this. Okay, 2x equals lambda, 4y equals negative lambda, right? So 2x equals negative 4y. Y equals negative 1/2 x. So we have the line y equals negative 1/2 x. that comes out of this process. Okay. Well, also, y has to equal x minus 3 because you got to be on this constraint path. So you're going to be able to find this point. Got two simultaneous equations that solve for x and y. Solve this system. You get plenty of ways to solve it. You've had linear algebra, you know how to solve systems. Use matrices if you want to. Matrix equation, inverse, all that stuff. But this is really simple. You get 3 halves x equals 3, so that x equals 2. And then y equals, no, it's not negative 1 half x, negative 1. Does it make sense? That this might be the point 2, negative 1? Well, in terms of the graph, if this is 2, this could easily be negative 1, right? But probably not. Probably not at the point that's indicated, which is on the curve where z equals 4. Okay? So I'm going to say this is not really on that curve z equals negative 4. Oh, dang. It is on the curve z equals negative 4. How did that happen? I mean, I drew this really sloppy graph that wasn't even to scale. And then I drew a line that was to a completely different scale. And the stupid line turned out to be tangent to the level curve z equals 4. What's the probability that that would happen? Okay, I didn't plan it that way, I promise. It's just fate. Okay, it's just another remarkable coincidence. One of the remarkable coincidences that occurred 40 years ago, 50 years ago, I was teaching over in the mechanical building where they had these desks with these little sloping places to put your hand and write. It drove left-handed people crazy because they were right-handed people. Anyway, I was just fooling around, tossed a piece of chalk. It was in class, but we're chalk at people and stuff. I was still playing intramural football, So some guys in class, and we kind of had fun in class, but we learned some calculus, so those are pretty good. So I threw the thing, to, throw it in the wastebasket. I probably tossed it overhand, okay? Because it's a piece of chalk broke, and then it flipped it. Well, I arced it a little too much. It hit the ceiling, dropped on one of those desks, and stayed on it. That's almost impossible. If I'd have been trying, well, I wouldn't even try it. It's just ridiculous. You could maybe hit the top of the desk, but how do you stay on it? The desk is sloping away from you. The chalk is moving away from you. Okay? Well, this is about equal to that coincidence. All right, well, color commentary aside, now the bigger coincidence would have been if the chalk had broken in two and one of the pieces had gone into the trash can. I've never seen one quite like that, but it didn't happen. Okay, 2, -1 turns out to be x equals 2. Oh, wait a minute, hold it. No, I'm right. Oh, okay. Relay what I said. It isn't. Okay, x squared is 4. 2y squared is 2. I was thinking it was 2 and 2 made 4. But since I don't even know that much, I thought that we'd had a remarkable coincidence here. Okay, so we almost had a remarkable coincidence. Okay, so what happens? Equals x squared plus 2y squared equals 6. So instead of hitting the z equals 4 curve, if everything was to scale, this would hit the z equals 6 curve, which is between z equals 4 and z equals 9. Okay, a little closer to the z equals 4 curve. So we'll indicate that. The z equals 6 curve the line would intersect the z equals 6 curve. At the point 2, -1. Okay. So what part of that makes sense to you and what part of it doesn't? Do you even believe it? What we have is p equals x squared plus 2y squared was our objective function. Our objective was to optimize this function. Okay. Or y equals x minus 3 was an example of a constraint function. Now we want to do this for an objective function. We're going to call the objective function f of xy. We're going to call a constraint function And I'm going to write the constraint function like this: y minus x plus 3 equals 0. So the constraint function is y minus x plus 3. Whatever the constraint function is, it might be on two sides of an equal sign. Bring it over onto one side of the equal sign and make it 0. Okay? So the constraint function is a level curve of this function of two variables. Okay? So the constraint function will be g of x, y. The blue circle circles the constraint function, circles g of x, y. So there's our general procedure. We can summarize this by saying the gradient of f is equal to the gradient of g. It is a multiple of the gradient of g. Just making sure my notation's consistent with the textbook, okay? It is so far. Okay, gradient of f equals lambda times the gradient of g. That's exactly what we've done, isn't it? Okay, well, we can take all this away because that's what we just did the calculations. And you can see that what we've done is we've taken the gradient of f, get the 2xi plus 4yj in our example, right? We didn't really do the gradient of g. I just asserted that the slope was -1, which is obvious from the straight line of slope 1, right? I could have done the gradient of g. Gradient of f was 2xi plus 4yj. The gradient of g would be the gradient of y minus x plus 3 equals -I plus j. Now, I happen to use I minus j, okay? But that doesn't hurt because I minus j is parallel to I plus to -I plus j, okay? Just multiply the I minus j by -1, you get negative I plus j. Okay, so it's negative I plus j here. It is negative I plus j here. It was I minus j here, but they're parallel. And the whole thing is your constraint, your idea is that the two gradients should be parallel. Okay. Then the gradient of f equals minus gradient of lambda times the gradient of g. Gives us this, and this gives us the same equations we got before, except there's a negative sign involved. Okay. But when you solve for lambda, when you solve for x and y, you're going to get the same thing. You can work it out. So what's our process? Well, there it is. Okay. Well, you get this. So in summary, gradient of f equals lambda gradient of g. And g of x equals 0. Give us the solution, which is just a point. Gradient of f equals g is 2xi plus 4yj equals lambda times negative I plus j. And this, well, that gives me three equations. That's three equations and three unknowns. One of the unknowns is lambda. Sometimes you want to solve for lambda, but usually you just eliminate it. So you'd solve for y and x. You eliminate lambda easily in this case. You're going to get negative 2x equals 4y, which is going to give you y equals x over 2, negative x over 2. Okay? You're going to get this. I'm going to write the lambda thing. That's your general method. key to understand and to apply the method is to understand that this equation is a vector equation. Means your I components have to be equal. That gives you an equation. Your J components give you an equation. So this actually gives you two equations. This is your third equation. You have unknowns, lambda, x, and y. Okay. Now, if this bug was moving around in 3 dimensions on some g of x, y path, and it doesn't have to be a curve. It doesn't have to be a straight line. It's a general curve. Okay. You're still going to have g of x equals 0. That's going to be one of your equations. That's one. In 3 dimensions, you have I, j, and k components. So that this equation becomes 3 equations in x, y, and lambda. Okay. Now, sorry, x, y, z, and lambda. Got a question? Yeah, I was careless. Incidentally, I'm often careless. This time of the year, it grows exponentially. I can't control it. It always happens. And I think it's around the time stuff starts getting into the air. They do have some allergies. Okay. So if you see me walking around catatonic, dropping things, walking into walls and stuff, just ignore me. But do be aware that I'll do stuff like that. I do it too often anyway. But never gets completely out of control because I always check myself. Except this time. All right. So again, what I'm saying is, if you have an f of x, y, z and a g of x, y, z, well, that just means that this gives you 3 equations, and g of x equals 0 gives you a 4th equation, which is good because you can try to find x, y, and z in lambda, right? Usually you eliminate lambda first because it's x, y, and z that you really have to. Okay. And that gives you your optimal point, whether it be a maximum or minimum. Let's see if I got anything right on. I'm not going to work out the details of this because in light of what I just said, I'd probably screw it up somewhere. Let's say that I'll stick to temperature functions. We see examples of other functions optimizing profits, optimizing this, that, or the other thing according to constraints. Okay, just arbitrary polynomial, secondary polynomial in x, y, z. So that is going to be a quadratic surface, but it's going to be rotated. Actually, it's probably not going to make a lot of difference here. Okay, and your constraint curve is x squared plus y minus z plus 4. If it's just x plus y minus z plus 4, it would be a plane because that's all linear. But this is a bit different, okay? In 3-dimensional space. Okay. So your del F equals lambda del G. Okay. Perpendicular to constraint is perpendicular to the objective to the level curves. What's that give us? Well, del F is 2x plus 2y I plus 2x plus 3z j plus 3y plus 2z k. Del G is 2x I plus y plus j minus k. Del F plus lambda del G tells you that the I component of del F is equal to lambda times the I component of del Y. So 2x plus 2y equals lambda times 2x. Similarly for the J component, 2x plus 3z, 2x plus 3z equals lambda times 1. And then 3y plus 2z is a coefficient of k. It's lambda times a coefficient of, well, of k here, which is negative 1. So you get 3y plus 2z equals lambda times negative 1. This is 3 equations and 4 unknowns, x, y, z, and lambda. What's the fourth equation? It's g of x equals 0. G of x, y, z equals 0, which is x squared plus y minus z minus 4 equals 0. There's 4 equations. And they're pretty easy to solve. I mean, these equations are all linear except for this one. Okay? Caught that out of the corner of my eye. I wasn't sure if you were asking a question or just tell me it's okay. All right. So that gives you a method that's not, you can follow it mindlessly or you can think about what it means. Try to think about what it means as you're doing it. Okay. And again, what it means is the direction perpendicular to level curve is this, it's your del F. And the direction perpendicular constraint is del G. If the perpendiculars are parallel, then you fit the optimal point. Okay.